All right, welcome everyone. Settle in. Today we're going to be diving into one of the most ambitious engineering projects ever conceived. We're talking about a city that literally builds itself on the moon. We're going to break down the blueprint for the entire lunar supply chain, piece by piece.
So here's our lesson plan for today. We'll start with the big idea, this concept of a self-growing city. Then we'll get into the nitty-gritty logistics, getting there and actually staying alive. After that, we'll look at the workforce, what the factory's building, and finally, how you power the whole shebang. So let's get started.
Okay, our starting point is a statement from Elon Musk that is by design, both incredibly provocative and, let's be honest, a little bit vague.
Now that phrase, self-growing city, it immediately brings to mind all sorts of science fiction, right? Something organic, spreading across the landscape. But from an engineering and logistics perspective, what are we really talking about here?
Well, let's be clear. The term is a hint, but it's not about biology. No. Self-growing is about creating a completely automated industrial ecosystem, a city that can expand itself using local resources. So this is really the core concept we're exploring today. It redefines growth as a technological process. You have AI guiding an automated, robotic workforce to build out a full supply chain from mining lunar rock all the way to manufacturing finished products. This is the engine that makes the whole thing self-growing.
Let's move on to our first big logistical challenge. Before you can build anything, you have to solve two really fundamental problems. How do you get there, and where do you live?
To really get the scale of the problem, let's look at the past. This was the height of the Saturn V, 111 meters tall. To this day, it's one of the most powerful machines humanity has ever built, an absolute marvel.
And think about this. All of that incredible power, all of that engineering, and what it delivered to the lunar surface was this tiny lunar module. It was just enough to support 2 people for about 3 days. That right there, that illustrates the core issue of space travel, the absolute tyranny of payload mass. Getting even the smallest things to the moon is just incredibly difficult.
So, the proposed solution is, of course, Starship. Its reusability, well, that's the key. That's what could completely change the economics of space travel. Now, we all know it's still very much a work in progress, but it's the foundation this whole plan is built on. But see, Starship has this dual purpose that's just brilliant. Once you unload its cargo, the empty propellant tank gives you a massive habitat. We're talking about 1,000 cubic meters of internal volume. That's more space than the entire International Space Station. All you need to do is just bury it under the lunar soil for protection against radiation and micrometeorites, and boom, instant housing.
Okay, so we've got our transportation and we've got a place to live. But who is going to do all the construction work, the digging, the assembly? The answer isn't astronauts in big, bulky suits. The plan for the workforce is actually inspired by this classic sci-fi concept called a von Neumann probe. The basic idea is you create robots that can, build more robots. It's about self-replication.
And this process, this is the key to what self-growing really means. It's an industrial replication loop. You start by mining the local materials. You use an automated factory to make new parts, new robots, and then you just expand and repeat the cycle, all without direct human intervention.
So, the robots are ready to get to work. What's their first big project? It's not building houses, surprisingly. The first thing they're building is a factory for a very specific and very valuable product: orbital data centers.
See, SpaceX's plan centers on solving the hardest part of the equation, getting things off a celestial body and into orbit efficiently. And it turns out, the moon is the perfect place to do that. And this is why. Just look at this chart. Look at the immense difference in the energy required to escape Earth's gravity versus the moon's. It's not even close.
So the crucial point here is that because the moon's escape velocity is so incredibly low, you don't actually need rockets at all to get things into orbit. You can use something way, way more efficient.
And this is that solution, a mass driver. It's basically a giant electromagnetic launch system, a railgun really. It flings payloads into space. It doesn't need any fuel, just a big steel rail and a whole lot of electricity. Okay, so let's move to the final piece of the puzzle. An automated factory and a massive electromagnetic launcher, they're going to need a truly colossal amount of power.
This is the ambitious solar panel manufacturing goal Musk has set, 100 gigawatts per year. Now, to put that into perspective, that's about 1/5 of the entire electricity generation capacity of the United States produced every single year. It's just a mind-boggling number.
And here's the kicker.
Building them for the moon is actually much easier. You can strip away most of the weight and complexity because you don't need to protect them from weather. There's no wind, no rain, no hail. They become incredibly simple. So, when we combine all these elements, we get to the ultimate vision behind this whole project. Tesla calls it amazing abundance. When you have near-limitless cheap energy, automated labor that builds itself, and automated transport to get things into space, you can essentially build anything.
And that leaves us with a final thought to chew on. If the physical constraints of labor, energy, and transportation are solved, what's the only bottleneck left? It's our own imagination. Thanks for coming today.